All right, welcome everybody. My name is Milioto, and I will be presenting in the name of University of Bonn, real-time semantic segmentation of crops and weeds for precision agriculture, leveraging background knowledge in CNNs. That title is a mouthful, and we regret it, but you're probably wondering what it's all about, so let's get to it. And there are very few things that we can all agree on, but one of those things is definitely that food production is of critical importance to human survival. And crops are a backbone of food production, and thus it's very important to maximize or even increase their yield. One of the most important tasks, keeping the yield high, is the process of weed control, which means eliminating all of the threats to the yield. So let's have a quick look at the state of the art of weed control right now. At the top, we can see conventional weed control, which is single-dose herbicide spraying. This has the advantage that it has a very high throughput, but its main downside is that it has a high environmental cost, and it comes at the cost of herbicide resisting in the long term, which makes it unsustainable. At the bottom, what we have is the state-of-the-art of a typical organic farm, in which the weeding is performed manually by human workers. This is very labor-intensive, and it has a high monetary cost, which means that it also doesn't scale very well. Following up on Ronnie Brooks' remarks yesterday in the plenary, this is also a job that we probably don't envision our kids having in the future. So how can we improve the state-of-the-art of weeding? And since we are ICRA, you probably guessed that it was robots. So what we can see on the right is a ground robot and an aerial robot that are doing an autonomously run over the field, analyzing the camera feed and analyzing the semantics of the field so we can detect the weeds and send the ground robot to kill them reactively. So how can this help organic farming? The goal is then to help avoid using herbicides indiscriminately through selective weeding. On the screen, we show two of the many examples of actuators that can be used in a robot to perform selective weed control. Many of you may also be aware of the work done here at QUT with many more of these actuators. On the left, we show a mechanical stamping tool, which after detecting the stem of the plant, can direct the pneumatic actuator and kill it reactively. On the right, what we have is a selective sprayer, which, depending on the type of weed, can spray a small dose of the right herbicide in order to put less herbicides in the soil and in our food. So what do we need for this? What we need is a robotic solution that is perception-based, that can navigate the field autonomously, and can recognize for each image in the camera feed of every robot, pixel-wise mask of what is a crop, what is a weed, and what is the background in the image, so we can direct the weeding tool. So this is what our approach is going to try to do. We're going to try to run semantic segmentation of crop, weed, and background, which means that for each pixel in the image, we will going to have a mapping to one of these three semantic classes. The main challenges for this are that because we are doing weeding and because we have a robot in the pipeline, we need it to work in real time, which is challenging. It also needs to be very accurate because we don't want to kill crops which are valuable. It needs to be robust, and this is a key aspect of the approach because you want to be able to ship this robot everywhere. So you need it to be consistent even under changes in the environment and in the soil conditions, in the weather and lighting conditions. And you also need it to benefit from limited training because the world has the soil and the weather and the lighting conditions has a very high variance, and so capturing data from the whole of this distribution will be really expensive and inconvenient, especially when you take into consideration that you need to target several types of crops. So let's have a look at a previous approach, which is based on a traditional vision pipeline. This starts by a pre-segmentation of the images into vegetation and background areas. This is done by using traditional computer vision methods. Then we proceed to a calculation of several input representations of the original images, from which we extract key points in the vegetation areas, and we use those extra representations to calculate several hundred features that experts in the field have designed that are robust to detect plant features. Then you run it through your favorite classifier for each patch in your feature space. You apply some tool to get some context information, such as a conditional random field, and you get an output such as the one you see here. Now, what are the main disadvantages of this approach? Well, the main disadvantages of this approach is that it contains this step, which is very, very hard to automate, which means that it needs a suite of hyperparameters to be able to work well in each new field, which means that basically in the pipeline right now, what you would have to do is to ship a grad student with each robot, which is kind of inconvenient. It is also has a very lengthy design process, which means that we have to manually calculate each of the features. It is slow to run, because even when designing the feature extractor in CUDA code, it takes 1 or 2 seconds per image. And at last, it usually relies on very expensive near-infrared information, which we want to try to avoid to use. This is especially critical for the pre-segmentation step, which we're trying to get rid of. So, as you probably guessed it, given the number of papers in this conference, the state of the art for this is using a deep learning pipeline. This takes advantage of the current advances in computer vision research, and it exploits well-researched semantic segmentation models that can be trained end-to-end from a semantic segmentation dataset for the task. And it also features no feature design time, which is convenient for us. And finally, they are also very good at getting context information due to having a large receptive field, which is very convenient when you're trying to get rid of all of these expensive tasks, such as the post-processing with the national random field. But unfortunately, not everything is sunshine and rainbows in deep learning world, and these approaches are very, very data hungry. And this is very inconvenient for us, because to capture the whole of the variance of our data distribution, we will have to capture thousands and millions of data samples from all around the world, given that the conditions in the soil are going to change with distance, and this is very inconvenient for us. And also, pre-trained models in other data sets tend to help the generalization, but given that you also need to train a data set that has a huge variance in the validation set, even if you use a pre-trained model, if you don't have enough variation in your validation set, you will overfit to your model, to your training set. And finally, one of the other disadvantages that it has is that these models are usually huge, and we want to try to make them more computationally efficient. So wouldn't it be great if we could combine the best of both worlds? And it turns out that we can. So what we're going to try to do is we're going to try to use these extra representations, which are calculated by the experts in the task, and we're going to feed them to a convolutional neural network. In this case, what we're going to try to do is by using these extra representations that we can see here, such as different vegetation indexes, such different color spaces, and different textures applied to these other representations, we're going to put them all in a depth 14 image that we feed to the CNN, and we are going to pass it through a lightweight, deep convolutional neural network that we design. The main advantage of this is that experts can encode their knowledge throughout all these years that they have been doing this before deep learning into the deep learning pipeline, and we can direct the attention of the CNN when we learn the features from the random initialization to look for features in places that can be directed by these extra representations. This is basically a technique that is doing some sort of data augmentation, but also at test time. And what it's doing is projecting the images from the original domain to a domain in which the CNN can look for very rich and robust features to changes in conditions. The other side effect of doing this pre-processing and extra representations of the images with the background knowledge is that we can design our CNN to be very computationally efficient. This CNN that we designed, which you can see the details in the paper, contains less than 30,000 parameters. And this is because these extra representations already take care of the texture of detecting the texture of the images, and we also only care about the geometry of them. So in order to experiment, we captured data throughout 3 years in all types of growth stages in different sides of the world. We have data from Bonn and Stuttgart in Germany, and we have data from Zurich under the project Flourish, which we are working on. And these data sets contain huge variations in the soil conditions and the weather conditions and different types of weeds. So the experiment one, what we show is that when we train the network in Bonn data, we obtain a gain of roughly 10% even in the same Bonn data, which means that it also helps the optimizer converge to a better value. And when we test in Stuttgart and Zurich, which is fields that we haven't seen before in the training data, what happens with RGB images is since we didn't have a good validation set, we tend to overfit to our field. And it doesn't happen when we use the extra representation. So we have a strong generalization performance. Another experiment is what happens when you want to regain a little bit of this performance drop that you lost during the transfer to a new field, and analyze how many images you need for the new task. And in this case, what we show is that, for example, in Zurich, test retraining with just 10 images, which takes roughly 20 to 30 minutes to generate, we can get the same performance as we will get with 100 new images in the RGB case. Finally, this approach runs in real time. And since the submission, we've been able to even improve these numbers by using different optimizers. And you can see it here running on an NVIDIA Jetson. And considering that we don't use the NIR information, near infrared information, we can also, for example, process data from a cell phone, which has only an RGB camera. As a summary, our approach allows experts to include background knowledge in the deep learning pipeline. We improve generalization consistently. And we need less training data, roughly 10% of what we needed before. And we can run online at 166 hertz. As a shameless plug, we've open sourced this, the code that we use in order to put this implementation inside, and we've made it general so that it can be used for a different suite of tasks for semantic segmentation. I'd like to thank you all for your attention, and if we have time, I'll take questions.
Yeah, I just wondered, are there other ways you could combine a traditional pipeline with deep learning methods? Did you think about other parts of the pipeline?
So we are working currently on other parts of the pipeline. For example, our following up paper to the traditional vision pipeline was taking into consideration the crop row structure using a Bayesian model. And we've successfully replaced that Bayesian model with an RNN. So we can basically also include the sequence information. So we're basically taking all of these bits of pieces that we had designed before and try to put it into these learned models, but also encoding what we know about what's useful about the task. So we know that the geometry is useful, so we try to exploit it, basically.